So I have a provocative question to kind of get things going here today. This is a question we've been talking around a little bit even in AP Calculus so far. We've been talking about secant lines, we've been talking about limits, and then we've kind of had in the background this idea of instantaneous rate of change or what the slope of the tangent line might be. And I always think of it as, a very curious student sitting around in Algebra 1, and they've learned about equations of lines. And in an equation of a line, we have the slope-intercept form, or maybe a point-slope form, where, if we have y equals 6x plus 5, we know that the rate of change is 6. The slope is 6, and it is 6 for the entire graph. A real curious student then, when you move on to talk about parabolas and all of a sudden you have these curved graphs, might be thinking or actually say, well, what's going on with this parabola? Because does the parabola have a slope? And, it seems like the slope would be different at different points. And at that point, Algebra 1 teacher might get a little bit nervous, might hit the secret button underneath their desk, and, the men in black type people come in with their suits and sunglasses on and take that student away to do a little memory clear and make sure that they don't ask like provocative questions like that anymore. But it's a very important question, right? Because we have functions that are defined in all sorts of different ways in math. And it would be important to be able to figure out the rate of change of all these different functions at particular points. If you think of all of the different types of quantities in our world that are modeled with sine waves, trig functions, quadratics, different types of polynomials, we want to have a way to figure out the rate of change of all of these different things at a point. And that's where calculus comes in. So the provocative question here is, what is the slope of the line tangent to the parabola y equals x squared plus 2x at the point 315? And there's nothing special about 315. We could talk about 1, 3, or any other point on this parabola. So the idea here is we are going to have to somehow think about what is happening as we take 2 points and bring them together. We have 315, and then we have another point down the road, and we bring them together, and we look at the limit as we bring those points closer and closer together. And so that's how we are going to get an instantaneous rate of change, which is also known as a derivative.
So there's a couple different ways that we can attack finding the slope of a curve at a given point, or the instantaneous rate of change, or the slope of a tangent line. So we can look at, if we've got some kind of curve here, f of x, we can look at a particular point. So at x equals a, we're at the point a, f of a. Okay, then we're going to look at a second point. And that second point is going to be h away from the first one. And so that puts us at, if we're starting at a here, this is going to be a plus h. So the distance between the 2 points is h. So this coordinate then becomes a plus h, f of a plus h. Now, if we're talking about the secant line, so this line here that goes through the 2 points, we can find the average rate of change, which is the slope of the secant line, by just looking at the change in y divided by the change in x, just the standard old slope formula. So we have the f of a plus h. So the y coordinate here in blue minus f of a. So the y coordinate of the red point. And we're going to divide that by the change in x, which in this case is just h. Now you could get that by doing a plus h minus a, but it eventually gets you to h. So there is no use of a limit here or anything like that. It's just average rate of change is this difference quotient. It's the change in y over the change in x. Now, limits are going to allow us to do things that are usually illegal, okay? That if we don't talk about limits, then this would become an impossible problem. We want to figure out the instantaneous rate of change. So we want to know the rate of change at one particular point. Now, we could bring this blue point closer together. Okay, we could bring it closer to the red point and see what happens. Ultimately, if we could get the blue point to be right on top of the red point, then we could figure out what the rate of change was at that point. But like I said, without limits, what we're talking about here is a denominator of 0. As we bring these points closer together, we're decreasing this value of h until eventually it's 0. So we can't figure out what it is when h is 0, but what we can look at is the limit as h approaches 0. And if we look at the limit as h approaches 0, it's a way to like beat the system a little bit. That's going to allow us to come up with the instantaneous rate of change, or the slope of the tangent line. So again, the idea here is that we're bringing these points closer together. We're looking at the limit as h goes to 0 of f of a plus h minus f of a over h. And this instantaneous rate of change, the slope of the tangent line, all these different words and terminology we have for it, this is the derivative. This is the derivative of f of x at the point x equals a. Okay, all of these are the same. Instantaneous rate of change, slope of the tangent line, derivative of f of x. And a short way to write the derivative of f of x is this f with a little tick mark of x, which when we say it is f prime of x. Okay, so this is one way that we can attack it. Now, so second way we can look at this is to have a similar scenario where we've got a curve f of x again. And we're going to think about our point here, A. Because again, we're looking to find what the slope is of the tangent line at that point, what the instantaneous rate of change is. But instead of going with a plus h, we're going to think of this now as just some other point x along the way. Some other value of x, could be any value of x along here. And so now this point, instead of being defined in terms of h, we're going to have just x f of x. And then our point at a is still the a f of a. Now, if we are looking at average rate of change in this situation between these 2 points, so again, we're looking at the slope of the secant. Now we've got f of x instead of the f of a plus h minus f of a over x minus a. And again, if we're thinking of instantaneous rate of change, there's no h involved here. Now what we're looking to do is we're going to take this point here, this value of x, and we're going to bring it towards a. So the difference in the formula here, if we're looking at the slope of the tangent, or the derivative, is to say we want the limit as x approaches a of this difference quotient, f of x minus f of a over x minus a. So one point of confusion for students usually early on is, there's 2 different formulas. How do I know which one to use? If I use the wrong formula, am I going to break something? And the answer to that is no. I think a good starting point is usually the first one, where we're defining it in terms of h, in terms of simplicity of what we're doing with the algebra. Some problems, it's easier to use the second definition, and some it's easier to use the first. And it's something you just kind of have to play around with. I'd actually recommend trying out both of them and seeing which one is most helpful for you. I'm going to go through a couple of examples here to show you how it would work, and I'll try and go with both of the scenarios here to give you a feel for what that looks like. We now have the means to come up with a solution to our provocative question that started this out here. So if we want to figure out what the slope is of a line tangent to the parabola f of x equals x squared plus 2x at 3:15, we're going to use one of our two definitions for a derivative or instantaneous rate of change and see if we can come up with what that limit will be, what that slope of the tangent line will be. So in this problem here, our a is equal to 3. This is the point where we're concerned about finding the slope of the tangent line at. That means our f of a, our f of 3 here is 15. If we put 3 into this function, 3 squared is 9, plus 2 times 3, we get 15 out. So let's use this first definition up here, the one in black. There's no real significance to why I'm using one or the other. Let's just check it out here. We're going to try and find the instantaneous rate of change at a equals 3, which is the slope of the tangent, which is also known here as f prime of 3. It's got a lot of different ways that we talk about it. And that's going to be the limit as h goes to 0 of f of 3 plus h minus f of 3 over h. So again, a in this problem is 3, and so we're just putting that in to this definition. So our f prime of 3 is going to equal the limit as h goes to 0. We're going to take the 3 plus h, we're going to put it in for x. So we're looking at 3 plus h squared plus 2 times 3 plus h. So that's the f of 3 plus h. Now, I'm just going to shift colors here because this is a point that sometimes gets students. We're going to subtract f of 3. Okay, now and in this case, it's not too bad, but I want to remember that we are taking this quantity away. So we have this f of 3 plus h out front here. This f of 3 plus h is everything that I have written down right now. And from that, I'm going to take away the f of 3, and the f of 3 here is 15. And I'm going to divide this by h. Right now, I know that I can't evaluate this limit because if I try and put 0 in here, I'm dividing by 0. So I'm going to work on this. I'm going to see what happens in the numerator when I do some expansion and see what cancels out. I always encourage my students, even if they're not people that like to write out a lot of different steps, it's important here to write that we are taking the limit each time so we don't forget that that's something that we need to do eventually in the problem. So we are going to need to eventually here take the limit as h goes to 0, write that down every time. Write the denominator down every time so you don't forget about dividing by h. When I square the 3 plus h up here, I'm going to end up with 9 plus 6h plus h squared. It's my 3 plus h times 3 plus h. I got 2 times 3, which is 6, and then 2 times h. And then I still have my minus 15 here. We're going to divide all that by h. In the numerator, I've got a 9, a 6, and a 15 that conveniently add up to 0. So 9, 6, and 15 add up to 0. I'm going to add my other like terms in here. I've got h squared plus 8h over h. Notice all of the terms that do not have an h in them have mysteriously canceled out. And so I can factor out an h out of my numerator. And that's great because when I factor out the h, it will cancel the h that's in the bottom that's causing me problems. Now I'm at the point where I can actually evaluate this limit by taking 0 and plugging it in here for h. And so we find that f prime of 3, our instantaneous rate of change at 3, our slope of our tangent line, is equal to 0 plus 8, which is 8. So this number right here is significant. This is the derivative. This represents the slope of the line tangent to this curve at this point. Okay, now usually a good follow-up question would be, what is the equation of the tangent line? what is the equation of the line tangent to f of x at 315? So now we know the slope is 8, and we have a point that is on this tangent line, 315. And so we're going to go with some point slope form. Y minus y1 equals m times x minus x1. We plug in our point, the 315. So we've got y minus 15. The slope here is 8. Okay, that slope is the derivative. And then I'm going to go times x minus 3. And so this is getting me that slope of that tangent line. Okay, now, is the slope going to be the same everywhere on that parabola? Absolutely not. It's going to change. On one side of the parabola, we're going to have negative slopes. On the other side, we're going to have positive slopes or positive rate of change. And at the vertex, the slope is going to be 0, right? We should have a horizontal tangent at that point.
What does this all mean in terms of the graph? So we've got f of x equals 2, or x squared plus 2x here. And we have this point that we are really concerned about at 315. So let's look at 315. So we want to know the slope or the rate of change at this point. Now, we found that that rate of change was equal to 8 and came up with this equation of a tangent line. Y minus 15 equals 8 times x minus 3. And when we graph that tangent line, you can see that right away it looks like the graph of the parabola here has one point of contact with this blue line, that it is indeed tangent to the curve at that point. And the more that you zoom in, the more apparent that becomes. It really looks like it's almost the same as the parabola within a really small range here. So we have y minus 15 equals 8 times x minus 3. So Desmos, being a great program that it is super powerful here, right? So I can just set up an arbitrary point on my parabola at a, f of a. So I'm going to add a slider in on here. It's going to allow me just to take that point and move it along. So we said that f prime of a is a way that we can represent the derivative. And Desmos knows all about this. So we're going to say that m for slope, is equal to f prime of a. And see, what this is telling me now is at any particular point, at any given value of a, Desmos right now is spitting out what the slope of that tangent line is. So if we think about the tangent line having to go through the point a, f of a, and having a slope of m, or f prime of a, however you want to define that, the equation of the tangent line is always going to look like y minus f of a, that's our y coordinate, equals the slope. So you can use m, or you could say f prime of a here, times x minus a. And so this is getting us now a tangent line to the curve at any value of a. And as we move this slider along, you can see that the tangent line moves with the point. Okay? Now, there is nothing special here about our f of x. This isn't the only f of x that this derivative process works for. We could type anything in here, and it's going to come up with the tangent line for us. So let's say that we have sine of x. Now, we have a kind of a bad window setting here. So let's take this down a little bit, change our y values. Okay, so we have a standard sine wave, and we can watch as this tangent line of the curve moves along the sine wave, which is great fun. So you can set something like this up in Desmos really quick by just having a space for f of x, defining the point a, f of a, making your slider, establishing what the derivative is. And again, we can leave this line out. We don't even need that in there. We could just type f prime of a right into this tangent line equation, and it's going to produce the same result. So that's what the tangent line looks like on the graph, and how we can get it to move around and use some of the features of Desmos and sliders. Clearly, there's a lot we could talk about with derivatives, more than you can ever fit in one semi-short video here. And so In the next video that I make, I want to look at some different examples of figuring out the derivative using the definition of the derivative, and also consider the deep thoughts here that could we come up with a general formula for finding the slope of the tangent line at any point a f of a on a curve y equals f of x. Desmos can do that for us. We just saw that. Is there a way that maybe we can use those definitions to come up with a formula so that we wouldn't have to figure out the derivative at each individual point? We can maybe do it in general. And so those are some ideas that I'm going to be looking to explore in the next video. Also going to look at some square root functions, some rational functions, what those would look like with the definition of the derivative.